Hello everyone, we are Shiva and that is Varun. So today we'll be presenting a project titled Drift Aware Bike Demand Forecasting using GBFS mobility data. So in this project, we built a system that forecasts how many bikes are available at each station just 5 minutes into the future. And the good part, or I'll say the exciting part for us, was that this neural network model can monitor itself for the model drift. We'll go in depth in later slides. So now we'll move on to the introduction tab. So yeah, so bike sharing systems like Bicing, which is like a famous bike sharing system in Barcelona, or City Bike, which is the famous one in New York, or even we have one, B-Cycle here in Boulder. So these are now the essential parts of our daily transportation. So thousands of riders depend on these stations to pick up or return bikes throughout the day. So the biggest frustration for users is uncertainty. So you walk into a station and everything is empty, or you try to return a bike and all the docks are full. So these issues happens because the city behavior changes constantly. So how it changes? Your morning changes during your morning commutes, your lunch hours, weekends, events, and even because of the weather, the availability, everything gets affected. So what we planned on doing was to do a short-term forecasting, which can really improve this experience. So only if we can estimate how many bikes that will be available for the next 5 minutes into the future, the riders can plan ahead more confidently. So operators can use prediction, or even the operators, they can use predictions from this model to rebalance bike before stations turn empty or full. And our project exactly does that. So it predicts we have a very short-term bike availability using real-time data. And we also built a drift monitoring component so that the system can detect when the prediction model becomes outdated. Because the city patterns changes for a variety of reasons. As I said, it depends on the seasonality, and then it even depends on the weather and all other factors. So this is like the brief introduction for our project. Now we'll move on to the data and prep tab. So we used the official GBFS API, which is like an industry standard feed for the bike sharing systems. And then there are so many endpoints giving so many data, but we relied on only two endpoints. The first one being the station status JSON, which is like which provides you data about the real-time station data. That is basically the bikes, the dogs, and e-bikes availability, the capacity, and all those stuff. And this is the endpoint which we hit frequently. Uh, we hit this endpoint every 5 minutes to append new data. So that's one thing. And then the other endpoint which we used was station information JSON for the station metadata, which basically contains the information about the location, meta, capacity, etc. So we wrote a Python script that polls these endpoints every 5 minutes. So every poll returned 545 stations. So this data set grows rapidly. So after collecting the data, we cleaned it by uh, passing timestamps, merging data with real-time status, estimating capacity when needed, uh, sorting the data by station and time. And and I would say the most important part of the data and prep was the resampling thing, because you will be having so many station IDs, and each station IDs have data collected across various timestamps. So resampling them, arranging them in a way was like the important part of our data prep. And then moving on to the next tab, feature engineering, which will be explained by my team at Varun. Varun, you can carry
Yeah,
on.
yeah. Once the data was cleaned, we engineered features to help the model learn short-term patterns. First, we extracted time-based features such as hour of a day, day of a week, weekend indicators, and some important rush hours like mornings and evenings. I mean, these helps us. I mean, this will capture all these. Natural behavioral cycles or something like that. And next we added lagged features which represent the number of bikes at the station, like 5, 10, 20, 25. I mean, after 25, 30 minutes earlier or something like that. Yeah. We also calculated rolling averages and computed bikes in and bikes out, which shows if the bikes are arriving or leaving the station. A target variable is simple: the number of bikes available 5 minutes into the future. Yeah. Next, we move on to models and methods. Even though this is a time series data, the prediction horizon is very short, only 5 minutes. Because of this, because of this, and because our engineered features also encode recent history, MLP works extremely well, and it trains much faster than sequential models such as like LSTM. Yeah, our architecture was well, 23 input features and a dense layer with 64, 32, and 16 neurons, and a ReLU activation and a final output layer. We added Adam as an optimizer and trained using MSC loss. Our model performed very well. Our test MSC was around 0.24, meaning on an average, the model is off by a quarter of a bike, which is excellent for such a noisy and real world data. And next, when we move on to this results, in our results we show prediction versus actual comparison for several stations. And the model follows short-term changes closely and generalizes well across stations with different capacities. We also build a predictbikes.py script which loads the trained model and generates prediction for every station in the real time. This script takes the most recent snapshots, builds all engineered features, and outputs forecasts like station some station ABC or XYZ or something like that, and 12 bikes, 13 bikes available in next 5 minutes, something like that. Yeah. Next, when it comes to this, yeah, drift monitoring, continue.
Um, okay, before moving on to the drift monitoring, I would like to give again a brief 20-second review of what we done right now. So basically, we got two endpoints. We got data from those endpoints. We manually created features. Why? Because we wanted to predict the availability of bikes within the next 5 minutes, which is like a short-term temporal thing. So automatically your sequential data becomes a tabular data. So we introduced engineer features, and then we made some feature engineering, and then we cleaned our data, and then we feed into our MLP model, which is like the basic multi-layer perceptron model, and then we got a beautiful results. I mean, I believe it. Our model worked really well for the data. Since GBFS data is usually the real, it's like it mimics the real world data, and it's actually really noisy. So and
And by the way, I would like to add one point. Adding
Mhm.
all these extra features it just serves one purpose, to provide enough sufficient data for this LSTM model which we are training, and which this model is like trained for every 5 minutes, and it is predicting for every 5 minutes, right? So
Yeah.
for this purpose, all these extra features are added, and rolling averages and what do you call it, like lagged features are added to support this model. Yeah, that's what I wanted to say.
So now we'll move on to the interesting part of the project. So the drift monitoring part. So as we said, so we are hitting the endpoints frequently every 5 minutes, and we're getting new data. So, but we have to know whether the model works well for the new data or not. And usually the city behavior changes over time, and so because of this, we add a drift monitoring system. So we added a script called monitor drift.py. We added a code link in the website so you can go check our code. So what this script usually does is, it's basically it is a training time reference data set, and it has the most recent few hours of live data. And then uh, in our latest trend, features like hard, day of week, bikes in and bikes or show drift. This means the model should be retrained. Okay, so what basically happens is, you can see in the results, we found out there's been a drift in the data. So which means the model should be retrained soon, and exactly the kind of monitoring a real time production system needs. So this might happen because of due to a variety of reasons, as we discussed earlier. So because of the seasonality changes or the weather changes, the statistical distribution between the data, you'll be having the same features, we'll be getting the same data, but the statistical distributions of the new data that is arrived will differ so much, so that the performance of the model will affect. So, and we actually found out that our model found a drift, and this model has to be retrained. This was the main goal of our project. So, and now we
Yeah.
can go to the conclusion tab. So,
I mean, I mean, we can call this network simply a self-healing neural network or something like that, because as soon as it meets this required things, like if the accuracy drops by 10% or 20% or something like that, some kind of as soon as it meets some of the checkpoints, the model retrains itself automatically. Yeah, we can call it a self-healing neural network.
so and then the conclusion, I'll move on to the conclusion part. So to basically summarize what our project did. So our project shows the real-time bike availability can be predicted accurately using neural networks and the real-world GBFS data. So riders, they benefit from more reliable information, and then even the operators can proactively rebalance bikes. So, oh yeah,
Yeah, and
Varun, do you want to end on? Do you want to end? Yeah,
yeah,
you
I
can do
mean,
the ending. Yeah.
yeah, our drifting monitoring system ensures that the model stays reliable as pattern shifts over time. I mean, looking ahead, we plan to automate retraining using Airflow, expose the model through an API, and extend predictions to longer horizons like 10 or 20 minutes. I mean, this lays the groundwork for the real world self-healing forecasting pipeline for urban mobility.
Yeah. So yeah, this is our project. Thank you so much.
Yeah, thank you for watching our presentation. And this also consists of this code link. Yeah, this
Yeah, you
code
can go. You
this
can go. You
drive link.
can.
Yeah,
Mhm.
you can see all the files here which we have mentioned in our presentation, which we were talking about and which we referred. Each and every single thing is present here. Yeah,
Yeah.
this
So
is that
anyone with a link
predicted
can
bikes.
access all
Yeah,
the scripts, all the artifacts, everything. So you can just play around
everything.
with
Yeah,
it if you want to. Thank you so much.